Swayam Prabha. Digital India. Educated India.
Okay, so in the previous class, what we had seen is that a crystal is inherently anisotropic. Slip plane and slip direction make a slip system, and then management of defects is a means of strengthening the material. So basically, we started off with that theme, and most importantly, we found that the depending on the need, whether we want to promote deformation or whether we want to prevent deformation, the orientation of the planes of easy slip with respect to the maximum shear loading direction makes a difference. Therefore, it is important to orient the planes of easy slip along the maximum shear loading to promote deformation, and orient sparsely packed, that is not closely packed planes in the maximum shear loading direction to resist deformation, because these are the sparsely packed planes are the ones which would have a very high shear strength, and therefore they will not start slipping, they will not get deformed even at high shear loads, and therefore they will resist deformation better. So the orientation of these planes plays a very important role relative to the direction of maximum shear. So now we will see in some detail about some of the surface defects, which are like grain boundaries. There are two-dimensional defects, and we will see how the crystal defects interact with each other. So we will see first the types of defects again, and then how they interact with each other. So in copper, for example, you have an FCC structure, and then you have the slip systems 1, 1 bar, 0, 1, 1, 1. So basically, this is a family of slip systems. You know that this is the slip plane and this is slip direction. So it's a family of planes and family of directions. And critical resolved shear stress is 0.64 MPa, 0.64 MPa. That is the ease with which the material will slip if this particular slip system or the slip plane and slip direction is oriented in the direction of maximum shear stress. So the material will behave dead soft. Similarly, aluminum will show even lesser strength of 0.4 MPa. Nickel will show a strength of 5.8 MPa. Now compare with iron, molybdenum and tantalum, which are body centered cubic. If you take a body centered cubic material, then you have the close packed plane, but there is no close packed direction as such in these materials, and that is the reason why the critical resolved shear stress is much higher with body centered cubic materials compared to the face centered cubic materials. And that is why most of the so called ductile materials, which can be easily deformed, which are easily used for manufacturing wires, and many copper atoms were malleability. So you have copper foils, aluminum foils, nickel foils. So you have lot of malleability, very high level of ductility in these materials, that comes from this low critical resolved shear stress due to a large number of slip systems with close packed planes and directions. So what happens is, when you have loaded a material, so I have been talking about orienting a particular plane in the direction of maximum resolved shear stress. So let us calculate, or let us imagine how the shear stress would vary depending on the orientation of the plane. Let us see why you are doing a tensile test. So you have a uniaxial loading from top to bottom. So there is a vertical axis of deformation, and then if you take a arbitrary plane which is oriented at some angle with respect to the tensile axis, so here the angle indicated is phi, so the normal is at an angle phi with respect to the tensile axis. And so now S is the slip direction because that is in the plane of this, so the plane which we have considered, an arbitrarily oriented plane which we have considered is does contain this slip direction, whereas N, the normal, is perpendicular to this particular plane. So basically this angle phi with respect to the tensile direction is also the angle between the slip direction and the horizontal, right. So this lambda is the angle between the tensile direction and the slip direction, and so you have the shear stress as sigma, which is acting in the direction of tension. So what is sigma? Sigma is the force, the tensile force divided by the area which is perpendicular to the direction of tension. So the cross sectional area will be at an angle phi, and therefore you have the component sigma cos phi, right. There are two things. One is the tensile load and this area, right, this area. Now the component of the tensile loading in the normal direction to this plane is will be given by T cos phi. It will be given by T cos phi divided by this cross sectional area will give us the stress, because load divided by cross sectional area is the stress. So now to find the area of this particular plane, we need to find the area of the plane which is normal to this tensile stress, because we know the diameter of this bar or whatever we might be deforming. So it's not just this is the cross sectional area that we know, which is perpendicular to the tensile axis. So that divided by cos lambda will be the area of this particular plane. So now to find the stress acting on this plane, what we get is sigma cos phi divided by, that is load cos phi divided by area upon cos lambda. So that is how you get sigma cos phi cos lambda as the stress onto the on that plane. So now if this is the this has a certain value of shear stress. Now these are planes of easy slip, meaning these planes have got very low critical resolved shear stress. So the shear stress at which the slip will start taking place in this plane and in these directions. Now if we take this particular, if we align this plane with this particular geometric plane. So this is a crystallographic plane, this is a part of the crystal, but if you orient the crystal in such a way that this particular plane is coincident with this plane over here, then this plane will start slipping at a very low load. So the amount of load that you need to apply here, it will be much smaller than what you would need if this plane were not oriented in the same, or this plane did not coincide with the same plane here. Okay. So it's very important that the direction of this plane relative to the direction of this geometric plane is understood. If there is a big difference between these two, then naturally the resistance to deformation is going to increase. If this closed packed plane, which is a plane of easy slip, is aligned or it overlaps this particular plane, then the slip is going to be extremely easy. So material will behave soft or hard depending on how this plane is oriented relative to the geometric plane. So that is the most important thing. And if you take, if you maximize this, and you differentiate with respect to one of these angles, say phi, then you will find that sigma cos square phi is the maximum stress. When lambda and phi are equal, you will find that they are the shear stress is maximum, and therefore what you will find is that the orientation at 45 degrees with respect to the tensile axis will have the maximum critical resolved shear stress. So from a geometric point of view, the plane oriented at 45 degrees with respect to the tensile axis will have the maximum critical resolved shear stress. So now if this plane is oriented along that direction, meaning oriented along 45 degrees with respect to the tensile axis, then you will get the material to behave the softest. So the behavior of the material based on the crystallographic orientation of these planes is called as crystallographic texture. So what it means is the behavior of the material, either as soft or hard, depends upon how well the plane is oriented with respect to the 45 degrees plane with respect to the tensile axis, because that we know is the plane with the highest resolved shear stress, right. So if we have a very strong plane oriented in that direction, then our shear stress required to cause slip will have to be much higher. So that is the benefit of developing a so-called crystallographic orientation. Now in the context of the face-centered cubic crystal, it is called as cube on corner texture, because this is one corner. So these are all, each of these vertices are considered to be corners of the cube, and this is a plane which is essentially the diagonal plane. And so if you have the cube oriented such that the corner is resting on the surface here, then this plane will automatically come parallel with this 45 degrees direction. So this is some sort of textural manipulation by which you will be able to orient this plane in this direction, and that is why you get different grades of material in the market. You get a large number of grades of material in the market, where the application dictates what should be the orientation of this plane of easy slip relative to the direction of applied stress. So in some cases where you need it to be structural material, you would not like it to slip, and therefore this particular plane of easy slip you would not orient along the direction of maximum shear stress. On the other hand, wherever you need to do let's say forming of car bodies, for example, or a lot of sheet metal working is involved in making a number of products, in such cases you would like this plane to get oriented within the plane of the sheet to the extent possible, so that the flow of material is very easy. So where you want deformation, you would orient this in the direction of maximum critical resolved shear stress, or in the plane of flow. So wherever the material flows, as it is called. So here, for example, the material will slip, and therefore material will flow so as to cause permanent deformation. So wherever you need permanent deformation, you would orient this plane parallel to this, so that the permanent deformation happens easily, because the idea is to cause permanent deformation. So now let's have a closer look at the dislocations. I had told you that there is an extra plane over here which causes compressive loading at the top, because of the fact that this extra plane tends to compress the distance between the two layers of atoms, whereas here there is tensile loading, tensile stress developed, and so a stress field is developed with regard to a dislocation. And this plane, this extra half plane, tends to travel from one position to another. The representation of this dislocation, which is called an edge dislocation, is that the half plane is represented with a vertical line, and then the plane below which there is nothing, the plane where the half plane ends is you put a horizontal line. So 1 and 2. So this represents an edge dislocation that is shown over here. So this is the symbol for the edge dislocation wherever you whenever you want to represent an edge dislocation. Once it comes to the surface, as we discussed yesterday, it creates a step. So there is a unit step of slip which also has to do with the Burgers vector. The length of the Burgers vector determines the length of a unit slip, and at interatomic distance the close packing of the planes results in a lowest Burgers vector, and therefore this unit step of slip will be smallest when the Burgers vector is small, and the energy that is required to cause slip would be least if the Burgers vector is small, and that is why you have slip on closely packed planes. So these dislocations propagate and create a dull surface. We have seen that as a result of creation of steps on the surface. The same is created using a dislocation, a screw dislocation which propagates in that direction, and then finally it creates a step something like that. So the screw dislocation is represented by a line because the Burgers vector and the dislocation line are in the same direction. So you see the stress fields over here, and here it is depicted, the dislocation moment is depicted. So you had a step over here, and then you have a step generated here. So so basically it's the moment of dislocations that results in a permanent deformation or a permanent change in shape, because now after removing the load you can this structure does not go back to that structure. So once the dislocation has moved here, if you remove the load now, it is not going to come back to this. So in elastic deformation, yes, but this is therefore permanent deformation. So this dislocation which has come to the surface has permanently come to the surface. It is not that after removing the load it will go back and the surface will become as smooth and as polished as before. So that is the difference between elastic and plastic or permanent deformation. Dislocations have to move. The dislocation movement starts so that the permanent deformation takes place. You cannot bring a dislocation back to its original position once it has moved by 1 unit step of slip. So the plastic deformation or permanent deformation is something which results from dislocation movement, and that is precisely why we call dislocations as defects, because if you were to really cause deformation in a defect free crystal, if the crystal were hypothetically defect free, you would need 1000 times the stress that is needed to deform that material permanently, okay, 1000 times the stress that you encounter in normal practice, right. So the material would be much harder if it were free from defects, but the dislocations are the ones which make our job a little easier to deform the material to the shape we want and get the dislocations to move at a much lower stress. So once the dislocations have started moving, then as you see the creation of the step, so the dislocation movement results in a permanent change in the shape. So now this slip of this workpiece with respect to I mean in this plane is now permanent. So these 2 steps have been generated permanently. So basically what we are talking about is dislocations facilitating the change in shape of the material at a much lower stress, right. So now you have dislocations moving at a certain threshold stress which is called as the yield stress of the material. So there is a transition from elastic to plastic regime, and so the yield point is essentially the stress at which the dislocations just start moving. And so once the material has entered into the plastic deformation regime, about 5% of its deformation energy is retained internally, while the rest of the remainder, the 95% of the energy is dissipated as heat. So what it means is that you have dislocations already present in the material. We have already said that defect-free material is a hypothetical concept. So in all real life materials, you have dislocations, you have vacancies, and you have grain boundaries. So grain boundaries are two-dimensional defects. One-dimensional defects are the dislocations, and point defects are the vacancies or interstitials. And then when materials are plastically deformed, meaning there is a propagation of dislocation, there is movement of dislocations, then you have permanent change in shape taking place. And when you have permanent change in shape taking place, 5% of the deformation energy. What is deformation energy? The force required into the displacement obtained. So the amount of strain that you give to the material multiplied by the stress generated in the material will give you the energy required per unit volume of the material. So the product of the strain, that is extent of deformation, and the stress will give you the strain energy that is stored in the material, or strain energy that needs to be supplied per unit volume. Must be remembered that it's per unit volume and not the total energy that needs to be given. Because if you take a 1 cc of material, the energy is going to be different as compared to 10 cc of material. But the energy per unit volume, if the metal is the same, the energy per unit volume is going to be the same. So one has to distinguish between the total energy required and energy required per unit volume. So you need to multiply by the volume if you are to get the total energy for the entire tons of material which you are going to deform. Right. So now when you have a dislocation present, there is an atomic distortion takes place. As you see here, you have compression taking place there and tensile stresses induced here. So now there is a distortion of the lattice. Okay, there is a distortion of the lattice, and therefore you have stresses and strains which are introduced into the lattice. So even before you actually try to deform the material, the stresses and strains are already present in the crystal lattice as a part of presence of defects. So the strains extend to surrounding atoms and their magnitude decreases with radial distance from the dislocation. That is obvious. So now we go to the reasons why that 5% energy is stored. What stores that energy? Yes, the dissipation in the form of heat is understandable, because usually most of the energy gets dissipated in form of heat. But then the 5% energy is stored in what form? It is in the form of increased dislocation density. So if you have certain number of dislocations per cubic meter or per unit volume of the material, with deformation the quantity of these dislocations continues to increase, and this multiplication of dislocations takes place in the following manner. This is called as the Frank-Reed source of dislocation multiplication. So what happens is, initially you had a straight line dislocation, let's say an edge dislocation or whatever of the length AB, and now you have a stress acting, a shear stress acting in that direction, due to which the dislocation line bends. So it is anchored at A and B, but then because of the stress it bends like that, and then it goes on bending this way, it goes on bending that way. Now what happens is, as this and these 2 points come closer and closer together, the dislocation tends to get annihilated, in the sense that these will be of opposite signs, and therefore these 2 points get joined together. So what happens is, these 2 points get joined together, and so you retrieve the original dislocation and have another dislocation which was created as a result of the stress acting on this dislocation. So now you have again this dislocation ready to multiply. So now both these dislocations are going to multiply. So basically what we mean is that if you have a dislocation density of a certain magnitude to start with, as the dislocations go on multiplying because of the stress being induced, the dislocation density increases, and the consequence of dislocation density increasing is that the dislocations tend to come in the way of each other as they move. So if a dislocation is able to freely move within a crystal, then it is easy for slip to take place. I mean, you can have slip occurring very easily, but if the one dislocation comes in the way of the other, then one dislocation will block the movement of the other dislocation, and that is where you see an increase in the stress that is needed. We will see these details much later, but then that is the reason why we are looking at the dislocation multiplication. So once the dislocation starts moving, it doesn't move, it doesn't stop with just the movement of dislocations. The dislocations multiply as they move, and therefore with this there is a, if you start with x dislocations, x number of dislocations, the numbers can go to 10x after a certain amount of deformation, certain amount of strain. So we will see later what are the consequences of this multiplication of dislocations, but then the strain energy is stored in the material in the form of dislocation multiplication, so that 5% energy that is stored internally, as has been said, is in the form of additional dislocations which are generated. The rest of the energy is dissipated as heat. So now here we see a picture which is obtained using a transmission electron microscope. We will see the characteristics of these devices, how they function and how they reveal the nature of materials, what the materials contain, but then the transmission electron microscope reveals the dislocations which are present in the material. So they have sufficient magnification so that they are able to reveal the dislocation structure inside the material. So an in situ TEM, an in situ transmission electron microscope, is something that enables you to do a tensile test or enables you to cause some deformation as the transmission electron microscope is watching the movements of dislocation. So basically it captures live the dislocation activity. Normally what will happen is you take a piece of material, you deform it to a certain strain, you have the initial dislocation density which would have been captured by the transmission electron microscope. After some deformation, again you take it to the transmission electron microscope, you have another picture of dislocation density, and then when you match them with each other, you will conclude that yes, dislocation density has gone up. But in an in situ TEM, you are able to see actually the dislocation move as well as dislocations multiply as the deformation takes place inside the material. So you can really track in real time live. So it's like watching a cricket match live, right? So it's very important to understand the dislocation motion and how these dislocations multiply, how these dislocations interact to cause what is called as work hardening. So what we call as work hardening is the outcome of interactions between dislocations. I told you that dislocations, edge dislocations, are constrained to slip along a single plane. That is because the dislocation line and the Burker's vector uniquely determine a single plane. So once one dislocation is formed on a plane, it is constrained to move along one plane. Now imagine a number of edge dislocations multiplying and dislocation density increasing on that particular plane after a certain strain. So then these dislocations, so it's like moving through a crowded street. So if the street doesn't have any crowd, the street is empty, there is no one on the street, you can move at the pace you want to move. But then if there are too many people around, then at every second you have somebody or the other coming in your way, and therefore your progress is very slow. So basically you need much greater strength to push your way through the crowd and come out of the crowd. So that is what happens to a dislocation as well. So when there is a large number of dislocations present on a plane, the dislocation movement gets hindered because of fellow dislocations which are present on the same plane. And so these interactions happen similar to the interactions that happen with people moving through a crowd, through a crowded place. So these dislocations therefore manifest on a macroscopic scale in the form of work hardening. So material behaves harder as the dislocations multiply and interact with each other, stopping each other's movement. I told you that for material to deform permanently, dislocations have to move, right? Now, if you don't want the material to deform permanently, you don't want dislocations to move, then what do? You orient the planes where the dislocations or the planes of difficult slip. Just like you have planes of easy slip, you will have planes of difficult slip. Which are the planes of difficult slip? The planes having sparsely packed, the sparsely packed planes are the ones of difficult slip. So naturally the dislocations would need more stress to move in those planes. So either you create a higher stress by orienting the planes appropriately, or you prevent somehow the movement of these dislocations. So one way of preventing them is by multiplying the dislocations and getting them to come in the way of each other. So now that is why we call it as a defect management. Although the defects weaken the material, now you manage the defects in such a way, you allow them to multiply and then get them interfere with each other, get them to block each other's way, so that the movement of the dislocation gets impeded by the fellow dislocations. We also add interstitials. We have point defects in form of vacancies and interstitials. So these interstitials which are added also do the same job. They impede the movement of dislocations. So basically when we add carbon to iron so as to strengthen iron, what we are doing essentially is to get the carbon atoms which act as interstitials. So they are very small atoms. The atomic diameter is much smaller than the iron atom, and therefore these carbon atoms would occupy interstitial spaces in the iron lattice. It's let's say at room temperature it is body centered cubic. So the body centered cubic iron lattice would have carbon atoms occupy the interstitial spaces, and these carbon atoms are the ones which will impede dislocation motion. And that is how we say that strength has been added by addition of carbon atoms. So more is the carbon added, more is the strength of the material, and that strength comes from these interstitials impeding the motion of the dislocations. So you have defects which are present, you can't live without them. They weaken the material, but then you make sure that the act of weakening of the material is in some way compensated by the by addition of some alloying elements which impede their motion, and therefore you get a higher strength. So again this is how the dislocations interact. What we have seen is that there are stress fields which are created. So for example, you have an extra half plane over here. So there is compressive force at the top and tensile force at the bottom here. And now if there is a interaction at the same level and same plane at the same level, then compression comes together, and so the dislocations tend to repel each other. So similar to the same charge coming close to each other, two positively charged particles coming close to each other will tend to repel each other. Similarly, you have the two stress fields, the two similar stress fields repelling each other. So these two dislocations would generate a repulsive force on each other. So if you have many such dislocation combinations, if you have generated a large number of such dislocation combinations, then these dislocations would refuse to come together irrespective of the force you have applied. And so on a macroscopic scale, you will find that material is behaving hard. The material has work hardened, or it has hardened with strain, because earlier let's say only one dislocation was present, now you have two, and then these two are now trying to come together, are being pushed together, but then they refuse to come together, and therefore you have the material behaving hard on a macroscopic scale. But now imagine two planes which are at less than 45 degrees with respect to each other. and you see that this compression and compression is not exactly coming together. There is part of this tensile stress field which is also coming close to compression, right. But then if this angle is less than 45 degrees, still the hardening would be observed, because the repulsion will still be there, but then to a reduced scale. I mean, here the repulsion will be the maximum, here the repulsion will be slightly reduced because of the fact that there is an angle. So one plane is and this is on one plane, this dislocation is on one plane, this is on another plane, and when these two come together, the two stress fields are the ones which will repel each other. So, or if the dislocation there is some angular difference between the two compression stress fields, then also the repulsion will tend to reduce. So, if the angle is less than 45, the repulsion will tend to reduce, and therefore, the material will still tend to behave harder, but not as hard as this condition. What happens if the angle is greater than 45 degrees? You have compression and tension of the neighboring dislocations coming together. So, the compression field of one dislocation gets aligned with the tensile field of the intersecting dislocation or the interacting dislocation, and therefore, when there is an angle greater than 45, so 45 more than 45, they would attract each other, and therefore, they would annihilate each other. So, when their dislocations attract each other, it means that they would easily come together, and therefore, the material will tend to behave soft. The material tends to behave much softer. So, the deformation is resisted the most over here, little less here, and the least over here. Okay, right. Now, if you have dislocations where unlike stress fields come together. So, here we had like stress fields coming together at different angles. Now, let us see what happens when unlike stress fields come together. So, compression, tension, plane is the same, but then dislocations opposite directions come together. Then they make a perfect lattice, because now you can imagine that there is a half plane over extra half plane over here, and now there is another dislocation coming with an extra half plane at the bottom here. Then that extra half plane would well get added over here, and then the whole thing, this dislocation will become completely stress free. So, there will be no dislocation here. You will have the compression annihilated or eliminated by tension, and this tension eliminated by the compression stress field on the neighboring dislocation, and therefore, you will have a complete plane being generated here, and then you have perfect crystal as is shown over here. But now, if these planes are not on the I mean, these two dislocations are not on the same plane, but they are on parallel planes. Let us say these two are on parallel planes, then what happens? Yes, they will attract, but then here when they come together, what will be left behind will be a vacancy, a point defect will be left behind. On the other hand, if these the two intersecting or two interacting dislocations come together on planes which are not separated with respect to each other. So, now this shear plane and this shear plane are not earlier were separated. Here this shear plane and that shear plane are not they are separated, but then they have an extra plane of this dislocation and extra plane of that dislocation. So, there you will find that once the interaction is complete, they will leave behind a interstitial over here. So, you can create either a vacancy or an interstitial depending on the configuration of the shear planes. If the shear planes are away like this, then it will create a vacancy, but if the two shear planes are interfering with each other, that is this half plane interferes with this shear plane and this extra half plane interferes with this shear plane, then you get an interstitial. So, whether an interstitial will get created or a vacancy will get created depends upon how the interaction occurs and at what angle it occurs, what is the distance between the shear planes of the two interacting dislocations, whether they are separated, whether they are interfering, or whether they are in the same plane but aligned differently. So now what we have again seen is that if you now align this plane and direction in the such that the plane of easy slip, so this plane of easy slip comes in the plane of maximum shear stress, right? Plane of maximum shear stress, then you will have easy dislocation motion, and therefore you will get the material to behave softer. Now, if you look at the at what we were discussing, now here we have the yield stress, meaning the stress at which the material transitions from elastic to plastic, elastic deformation, temporary deformation to permanent deformation. So at yield stress, the dislocation just starts moving. So now if you look at the angle between the tensile axis and the basal plane, so now this is probably pertaining to a hexagonal close packed crystal, because the basal plane is one of the planes of easy slip in a hexagonal close packed crystal. So if you take an HCP crystal structure, then depending on the angle tensile axis and the basal plane, you may find that as the angle becomes 45, the yield stress reduces to the maximum extent, right, and then again it rises further. So basically, so even if you imagine this plane, if you imagine this kind of plane, so as the angle changes, so you have a, let's say, a plane which is a face of a cube. If the tensile axis is aligned along the face of the cube close to 0, the yield stress is very high. As it moves towards 45 degrees, the yield stress is much smaller, and then as it gets again perpendicular, then it becomes further high. So that is what is indicated in quantitative terms. So from an atomistic viewpoint, we have dislocations which are defects of crystal lattices built up of atoms, and so this is the atomistic viewpoint. And the continuum viewpoint is that dislocations distort the crystal lattice in their vicinity. They cause elementary stresses which can be treated as by the methods of continuum mechanics. So if you treat the entire mass of material as a continuum, not as being composed of discrete atoms being arranged in a particular order, then you can look at the stress fields, and you can treat the entire piece of metal as continuum with stresses acting as specific locations. Whereas from an atomistic viewpoint, if you take the bulk of material as composed of individual atoms, then you would consider dislocations as defects in the crystal lattice made of, and then you would look at the orientation of the crystallographic planes and these dislocation interactions, etc. So these are some of the points to be remembered with regard to dislocations. So you have the strains extending into the surrounding atoms, and the magnitude decreases with radial distance from a dislocation. So the stress field is a maximum, and therefore the strain field is also maximum in the vicinity of a dislocation. Now let us take interfacial defects, which are two-dimensional effects which are kind of grain boundaries, or there are twin boundaries, stacking faults, and phase boundaries. We will come to these definitions later. We have seen the concept of a grain where you have an orderly arrangement of atoms up to a certain point, up to a point where the orderly arrangement in some other orientation disrupts the orderly arrangement in one particular orientation. So you have these grain boundaries where you do not have any orderly arrangement of atoms, so the atoms are randomly arranged, so naturally they would not occupy the positions of minimum energy, and hence the grain boundaries are the regions of higher energy content. So now interfacial defects are boundaries that have two dimensions because they are surface. The grain boundary essentially covers the entire surface of the grain, and that's why it's a two-dimensional defect. And then they normally separate regions of materials that have different crystal structures or crystallographic orientations. When we define phases, we define them phase as a region of material having a homogeneous crystal structure. So when we said that you have iron dissolved in carbon dissolved in iron to form ferrite, then you have this a phase where you have a body centered cubic crystal structure with interstitial carbon atoms dissolved in iron to the extent of 0.02%, whereas you have cementite, which is another phase where the crystal structure is different as compared to the body centered cubic of iron. So if you take cementite, it's a product of a chemical reaction between iron and carbon. So Fe3C, iron carbide, is the chemical formula for it, and so the nature of this iron carbide is different from a body centered cubic structure of the of iron dissolving some amount of carbon. So basically, in a particular phase, be it ferrite, be it cementite, there is homogeneity in the structure, there is homogeneity in the lattice spacing, the layout of the atoms which are present in that particular phase, and therefore phase boundary is the one where this orderly nature is disrupted, that is broken. So you have a phase boundary as a two-dimensional defect once again, because the phase boundary being a region of mismatch results in further weakening. So you have grain boundaries, you have phase boundaries. Similarly, you have twin boundaries. Twin boundaries are the ones we will see what is mechanical twinning, but then you have just like deformation of a crystal by slip, deformation by another phenomenon called twinning. We will see that a little later, but then these boundaries are the ones which results in which are treated as defects which weaken the system. Phase boundaries, twin boundaries, grain boundaries, and then stacking faults. So you have you can visualize the crystal as being made of certain layers of orderly arrangement of atoms. So in case of close packed crystals, we had seen that you have ABC as the stacking sequence for FCC structure, or AB as the stacking sequence for a hexagonal close packed structure. So this stacking sequence is again broken or is disrupted by what is called a stacking fault, which again constitutes a defect. So let's say you have ABC as the stacking sequence, then at some point you have, let's say, plane C that is missing. So you have instead of ABC, you have AB, B, C, A. So some such sequence could be present, and that is called as a stacking fault. And so these are some of the imperfections in the crystal which result in boundaries. So which result in discontinuous or regions of discontinuity, right? So one of the most obvious boundaries is the external surface. So that is also a boundary between the chunk of metal and the environment. Let's say you take a cube of metal, then it has got 6 faces. So each of these faces are the boundaries of that particular chunk of metal, and so they are also external surfaces where you have atoms present on the surface, and they interact with the environment. So things like oxidation, corrosion take place on the surface because there is an interaction of the surface atoms with the environment. You have moisture, you have gases which are present in the environment which react with the surface of the metal. We see commonly aluminum, for example, never stays as aluminum. You always get it in an oxidized state. So the surface becomes dull after some time. That is because the boundary, which is the external surface of the chunk of material, reacts with the oxygen in the environment. So, this is one of the obvious boundaries. Surface atoms are not bonded to the maximum number of nearest neighbors, and therefore they are in a higher energy state than atoms in the interior position, because atoms in the interior positions are the ones which have a chance of occupying the position of minimum energy, whereas atoms on the surface do not have that opportunity. They would be occupying states of higher energy, and that's why they can get easily corroded or easily attacked by corrosive elements or moisture, oxygen, any other gases like hydrogen sulfide and something like that. So the bonds of these surface atoms are not satisfied. So those surface atoms whose bonds are not satisfied give rise to a surface energy, as it is called. So there is a surface energy associated with formation of this surface, these new surfaces, which are interfaces between the chunk of metal and the environment. So, so the surface energy is associated with the unsatisfied bonds which are present in the material. Now you have two types of grain boundaries. Let's say you have two grains growing in different directions, different orientations. So one lattice is growing in one particular direction, and the other lattice is growing at some inclination with respect to that direction. Now the grain boundary which will form at the intersection will depend upon the angle at which the two lattice configurations meet, the lattice directions meet, right? So now there is order in this direction, there is another long range order in that direction, due to which you have a grain boundary which is present here, where the angle subtended by the misorientation between the two lattices is very small. So that is called as a low angle grain boundary. Wherever there is a large amount of misorientation between the two lattice orientations, right, there you would call it as a high angle grain boundary. So the high angle grain boundaries are the ones which result in lot of accumulation of defects. Well, the low angle grain boundary means that the two lattice orientations would have been the same if the misorientation had been absent. So that slight misorientation is something that prevented the two lattice orientations being identical, right? So the low angle grain boundaries indicate that two lattices would have been the same. They missed that opportunity by a whisker, by a very small degree of misorientation. So the low angle grain boundary therefore will have very few defects, meaning in the form of dislocations as shown here. Okay, the defects arising due to mismatch between the lattice orientations manifest themselves as dislocations. So now there is a large amount of dislocation density at the grain boundaries. So when you have a large high angle grain boundary, the mismatch is more, and therefore the dislocation density in the high angle grain boundary is also very high. In a low angle grain boundary, the dislocation density is relatively smaller, right, because of the low mismatch. So now when we say that there is a stress field associated with each dislocation, there is therefore a strain field also associated with every dislocation, then we will appreciate the fact that higher is the dislocation density, larger is the number of dislocations, larger are the number of stress and strain fields associated with each, and therefore the total amount of stress and strain that is associated with each of these grain boundaries at higher angle is much more than the strain energy associated with a low angle grain boundary. So a high angle grain boundary has got a much higher strain energy associated with it. So now I was talking about strain energy being stored inside the material, and this is another way in which the strain energy is stored. One way is to multiply dislocations and have a large amount of dislocation generated in the material, and another way is to store this energy in the form of high angle grain boundary in the form of a large number of dislocations generated at the grain boundary. So when you subject the material to what is called as severe plastic deformation, okay, plastic deformation to extremely high strains, okay, the extent of distortion in the material, extent of permanent deformation in the material is extremely high. In that case, you will get high angle grain boundaries. That is because you need to accommodate the large amount of dislocation density that has been created by way of storing that strain energy generated due to the severe plastic deformation. So in severe plastic deformation, you create very large amount of strain energy, and that has to be stored somewhere, and therefore you need large number of dislocations, and this will happen when you generate high angle grain boundaries. So when the strain level is high, you get high angle grain boundaries. When you anneal the material, meaning when you heat the material, again I am using terms which I have not defined yet, but then one can therefore start with one kind of grain boundary and obtain another kind of grain boundary. So basically what I am trying to tell you is that through a certain manufacturing processes, through certain set of manufacturing processes constituting a manufacturing route essentially, you will be able to generate low angle grain boundaries, high angle grain boundaries, defects in specific planes, orientation of crystals. I was talking about orientation of crystals in specific directions. So one can generate these orientations in crystals, in planes relative to the direction of loading by using appropriate manufacturing route, by using appropriate manufacturing process. And the reason why this happens is because you manage defects, you manage generation of defects properly by subjecting the material to appropriate amounts of stress and strain. So you have a high angle grain boundary and a low angle grain boundary. So when you subject the material to large amount of strain, you have high angle grain boundaries being generated. And if the material is not very work hardened, small amount of strain, the degree of mismatch between the two grains is relatively low, you have what is called as low angle grain boundary. Similarly, you have grain boundaries like tilt boundaries. Similarly, so this tilt boundary is something which is talked about when in the context of edge dislocations. So you have a small tilt between two orientations, whereas the twist boundary in the context of screw dislocations. So now we understand why the grain boundaries are more chemically reactive than the grains due to the boundary due to this grain boundary energy that is stored there. And impurity atoms, which often create disorder in the orderly arrangement of atoms of a crystal lattice, they segregate along these boundaries because of their higher energy state. So these grain boundaries are able to accommodate these interstitials very well, right? Yes. So now we see that these misorientations. So there are using certain techniques like EBSD, okay, electron backscatter diffraction, you can get the misorientations at the grain boundaries. So you have these grain boundaries at different orientations, and you will see that there can be diffusion of atoms across a grain boundary, because grain boundary is the region of very high energy, very large amount of disorder, and therefore there are passages which are available in the grain boundary through which atoms can diffuse. So particularly the interstitial atoms can diffuse. So many of these grain boundaries, again grain boundary is a surface defect, and therefore this promotes kind of diffusion of atoms from one location to another. So we will see more of activity of these defects in changing the material properties, in changing the behavior of the material in permanent deformation of plastic deformation under room temperature conditions as well as under high temperature conditions. Vacancies particularly matter a lot when the material is deformed at high temperature. So that is the reason why we should study vacancies. So all these defects have a role in promoting permanent deformation in the material, be it at room temperature, be it at high temperature. So we will talk more about these, the role of these defects and the management of these defects in a few lectures to come. So we will continue with our discussion in the current class. Thank you.